All right, so we should be live now, but before we start, I do want to make a sound test. So, folks, if you can hear us all right, Anupam, maybe you want to say hi.
Hey, everybody.
If you can hear us all right, then give us a thumbs up, so we know the sound is working, and then we'll get the ball rolling here. You can hear us? Good. Okay. All right.
Awesome.
Good. So, Anupam, this is our last live event for 251 this semester. So this semester we taught the course together, and it was a real pleasure teaching with you. It was a great experience. And so we'll end it, I guess, with this conversation here. I want to get into your research, dive into your research a little bit, and then ask some other questions. We also got questions from the students.
Perfect.
I want to ask those as well. So let me start broad, and then dive deeper into your research. So first of all, I'm curious actually, how would you describe computer science? It's a huge field. It encapsulates many different things,
Right.
and I guess people have different perspectives on what computer science is. Is it a science? Is it engineering? What is it? What's going on?
Right.
So how would you describe computer science? And then how would you describe the role of theoretical computer science within that? And then how does your own research fit into theoretical computer science?
It's a sort of great question that sort of sets the stage for everything we do, right?
Yeah.
And so computer science is really understanding computation. And computation, as we discussed again and again in the course, is so many. It has so many facets and so many different angles that it's we can define it as the sort of processing of information, but this could be by almost anything. And as you said, we are all computers. And,
Yes.
So just understanding computation is how I view computer science as. And theoretical computer science is trying to understand the power and limitations of computers. And I think once put it in that sort of generality, it's trying to understand such a sort of amazingly wide range of phenomena
Right.
that I think it just blows my mind.
Yeah, like you say computer, but when people hear that, they think about like electronic devices that we use today. But as you said, computation is actually a much more general phenomenon. So yes, we are studying, the limits and power of computation, computers, but that means like really the limits and powers of the universe that we live in, like the laws of physics and things like this. So it's very fundamental.
And in fact, just recently there's been a line of work that people are trying to understand what these little mold, this slime mold, what's the computational power of that? How are they computing?
Yeah.
So it's like power and limitations, but also how and why.
Yes. It's actually funny, like me plug in 15155. This is a course that Pravesh and I created. It's called Computational Lens. And it's one way to describe it would be like it's kind of like 251, but for in a non-technical way, not with like the proofs and math way, but more like the more general way, more big picture view way. And the reason I bring it up is because like the mold example, Pravesh loves to give this example in the first lecture. Like, see these molds, they seem to be computing like shortest distances, paths, and it's quite amazing. Okay, well, anyway, so let's now talk about like how does your own research fit into this, big picture view of theoretical computer science?
And so it's the how and why part of theoretical computer science that my research fits in, because my research is in algorithm design. So I need to understand how can you compute things? And if there are limitations, why are there limitations? How do you get around some of these limitations in a different computational model? Questions like this drew me to algorithms. In fact, when I first started, I wanted to do complexity theory, which is to understand the limitations of computation.
Right.
But then over time, I realized maybe my interests were more towards the algorithmic side.
And, right. So, maybe like I can remind, like this is something that I mentioned in the first lecture, but it's good to remind the folks, like you could say at a very like high level, broad overview, like there are two main camps in like the foundations of theoretical computer science. There's like the algorithm designers. They're trying to always come up with faster and faster algorithms for problems. And then there are complexity theorists who are like on the other side of the coin. Like they're trying to show that no matter what algorithm you use, you need at least this much time, at least this much resource. And you are on the algorithm side, like you are the optimist, and you're trying to find better and better algorithms for important fundamental questions. And within that, if we go deeper now, within algorithms, because still algorithms is huge.
It's a huge area,
right? Like within algorithms, like what do you work on?
So I work on two main areas, I would say. One of them is approximation algorithms, which we discussed a little bit in the course, that life is tough and we have NP-hard problems, but we need to do something. And so approximations are doing the best we can, given the constraints we have of, let's say, efficiency of polynomial runtime.
Right.
And another thing that I work on quite a bit is online algorithms, or more broadly, what I say, optimization under uncertainty. That if my data is not available up front, and if it changes over time, then, for instance, requests are coming in one by one. I need to make decisions now.
So this sounds very similar to how DFAs are, right? Like, they get the input one bit at a time. They don't know when the input is going to end. Totally. And they get one scan through the input and they have to make a decision at the end.
Right then and there.
So how are these things related? I mean, I guess like we can also talk about streaming algorithms, which is kind of similar.
Exactly.
So how do you sort of contrast like DFA, streaming algorithms, online algorithms?
So DFAs are particularly simple versions of online algorithms. In some sense, when a request comes, a DFA has exactly one action it can take.
Right.
Whereas you might have decisions that you might need to make. So for instance, imagine a DFA where you see an A and you could go to one of two different states.
Okay.
Which state should you go to?
Okay.
online algorithms are trying to answer questions like that.
Okay.
Or your cache is full. So maybe I'll
Yeah.
give the sort of prime example of online algorithms. Your cache is full.
Right.
You need to get rid of a page in the cache to bring in a new page.
So would it be fair to say that in online algorithms, you're not necessarily limited with respect to space?
You're not limited with respect to space.
And with DFAs, like really you have constant amount of memory.
Totally.
With streaming algorithms, it generalizes a little bit. Maybe you have logarithmic memory, polylog memory.
Totally.
But I guess with online algorithms, is it true that often we're interested in like optimization problems? You're trying to optimize something.
Exactly.
And then we sort of, one way to measure the performance of an online algorithm would be to compare it to the best offline algorithm.
Absolutely.
Offline meaning, of course, you get to see the whole input as you wish. You can do whatever you want, and then you want to like give the best possible output. So comparing your online, so that's called the competitive ratio.
Or actually, maybe we should even call it the price of uncertainty.
Okay, good.
So imagine an algorithm which doesn't know the future.
Right.
So it's making decisions in the presence of uncertainty.
Right.
And then you compare yourself to the best algorithm that knew the entire sequence.
Right.
That was, like a future seeing,
Right.
a clairvoyant, if you will.
Nice.
Algorithm. And so that's the kind of questions we ask.
Okay.
How much do I lose out because I don't see the future?
Okay. So and that's approximation algorithms. We talked about online algorithms. What else?
What else? All kinds of algorithms I'm interested in, and it's very often driven by the questions that my students are interested in.
Okay.
So sometimes my students are interested in just fast algorithms for graph problems.
Right.
How to compute cuts in graphs.
Yes.
It's like, okay, let's work on that.
Yeah.
And and also I'm very interested in understanding metric spaces. And so that's something I worked on for my PhD.
Yeah, so metric embeddings, right? So let's maybe describe that a little bit, because I think it's a very interesting idea.
Absolutely.
So at a high level, what's the idea behind the metric embedding? Like it's an algorithmic technique, I suppose.
Absolutely.
Can you maybe describe that?
Absolutely. So it's this technique which says, suppose I have some distances between points. Say I have distances between words of how similar they are.
So this is like Hamming, like how many coordinates they differ at?
Say.
Okay.
Or you could have a notion of distance by how similar they are in meaning. And this is something that
nice.
Deep networks are very much interested in.
Yeah.
So now, if you gave me a notion of distance between points, and you asked me, could you embed these points into, say, three-dimensional space?
Like Euclidean space.
Euclidean space.
Right.
So that the distance between those points exactly corresponds to this abstract notion of distance that you have.
Right. So maybe, is it really exact, or is it like, close enough?
Exactly, close enough. Because
Right.
in many applications, the notion of distance that we've cooked up
Right.
is already kind of fuzzy and not exact. So you might as well distort distances by a little bit.
Right.
And you want to minimize this distortion.
So this sounds like a reduction.
This very much is a
This
reduction.
like you're reducing your original problem that doesn't seem to be directly related about distances between points. And you're reducing it to another problem, which is like about distances in Euclidean space. And then you're saying, well, I suppose you're saying like we know how to solve those Euclidean problems.
And then we will bring them back to the general case.
Right.
So I often think of us metric embeddings people as being kind of map makers.
Yes.
Because the world is this sort of complex three-dimensional thing. And what map makers try to do is to represent that on a two-dimensional surface.
Right.
We are taking
As
an abstract
accurately as
metric.
possible,
Exactly.
yes.
And there might be various notions of what accuracy means.
Right.
And that gives different maps.
I see.
So I view the analogy as being very much like that, and very much a reduction.
Yeah. So yeah, that's very nice. And one question there, like, can you give us like a prime example, like a poster child example for like this phenomenon. Like, here was a problem we didn't know how to solve, and then we applied this technique, this reduction metric embeddings, and we got a beautiful algorithm out of it.
So one example of this is for approximation algorithms, where we wanted to solve a variant of k-means, which is a common clustering heuristic.
Okay.
It's called k-median in this case, but it's a slight variant of k-means. It's not important, the details. And we didn't know how to solve that on a general metric space. But there are these very nice results which say any metric can be approximated, can be reduced, and this is the reduction is a randomized algorithm, but that's another detail, to a tree.
Okay.
And so now any metric basically behaves like a tree. And so we had to solve the problem only on trees, which was much easier.
I see.
And we could use a technique, dynamic programming, which the 251 students will see in 451, or maybe in 210 even.
210, yeah.
Yeah.
Absolutely.
So, it's simple dynamic program.
Yeah.
And this was like a 10-year long problem that people didn't know how to do. And then once you had the right techniques, it was
So when is this result from, roughly?
So this is from the late 90s.
Okay, sounds interesting. And I guess like reductions, as we've seen in the course 251, very important concept in computer science, but not just in, I think in science in general. It's what we use oftentimes. Reduce the problem that you have to something you know how to solve.
You know how to solve. This is one of these sort of general problem-solving techniques, which our students, I'm hoping, will take away, no matter what else they take away.
This is one of the things they should hopefully.
They should always remember.
I guess like other examples, like if you can take your problem and reduce it to SAT instance, like we have powerful SAT solvers out there. They could be very useful. Like, that's another example of this.
Exactly.
Any other examples we can think about?
So something that
like linear programming.
Linear programming. Yeah. That's what I was thinking. It's this super powerful language.
Yeah.
And if you can cast your problem as a linear program, which again you'll see in 451.
451, yes.
There you have it. You have linear programming solvers which are very powerful, which are very fast.
Or semi-definite programming.
Semi-definite
is now the more
programming.
fancy version of this. Okay, awesome. And another, I guess, thing that you're interested in is going beyond worst case analysis of algorithms, right? And I think this is very important because like this is most undergrads, CS undergrads, all they'll see is really like worst case analysis, right? And that's a good starting point, of course. And, it gives you ironclad guarantees. That's great. You would want to have that. But at the same time, practically speaking, it doesn't always correspond to reality as closely as we would like. So, we should find other ways to analyze algorithms. So what are some alternatives to worst-case analysis?
There are so many. In fact, I can point to a book out here, but we won't do that. It's like, it really depends on the situation you are in. So whenever faced with a problem, of course, it's really good to give a worst case guarantee. But then we go and say, well, how were these instances generated? Maybe we are trying to solve matchings. Right. But maybe you're trying to solve matchings on a bipartite graph.
Right.
The problem is easier.
Right.
Maybe it's a planar graph. The problem is easier.
Right.
Maybe it's a low-dimensional space,
right.
Euclidean space. The problem is easier. So also, maybe the data is being generated by some simple distribution,
right?
Some probability distribution that we understand,
right.
That we know. And like, for instance, what happens is when talking to people, you realize, you're trying to figure out which ads to place when on some, website, let's say.
Mm-hmm.
But the data is being drawn from just people, and people have these periodicities.
Right.
At 9 o'clock in the morning, you'll see a certain traffic. At 5 o'clock in the evening, you'll see a different traffic.
Right.
And so just learning what's making the data predictable,
right,
what's making it simple, makes a big difference in how well you can solve it.
But then the challenge is, of course, like accurately modeling real-world situations, and then even when you have the model, like finding a clean theory to analyze it, right? Like and like to be honest, like one of the reasons we focus on worst case analysis is because it's clean. Like,
it's very clean. There's no argument. You and I will agree on what the worst case is because it is the worst case.
Yeah.
But whether this is the real case, whether this is the case that's arising in practice, is something that we can argue over.
Yeah.
That also makes the area interesting because then we have these very interesting discussions about exactly what the data is coming from,
right,
and how to best model it.
Right.
But this, in practice, this is something that has to be done.
Yeah.
And maybe one other thing to mention out here is that sort of the algorithms, there is always a danger when working with beyond worst case analysis, is there's always a danger of overfitting to the assumptions we are making. So this is why a good discussion is important between people who are doing this, so that you don't fall into this trap.
Okay, so let me then ask this, since we're talking about like some relation to practice. Does your work have some practical applications? Hold on. Should a theoretical computer scientist in general care about practical applications? And what is in general, the connection or the interplay between, practice and theory? And how should that relationship be?
This is such a sort of great question. It's a minefield as well, so I'll have to navigate this carefully. But I think a computer scientist should care about practice.
Okay.
Now, whether the work directly, so I can say what my relationship to practice is. Very often my questions come from questions that people ask in talks, in conversations, very often from practical situations. Now, my job often is to abstract that out into a formal question that I can actually say something meaningful about, and then present those algorithms. And then often those algorithms are just theoretical algorithms. But in some cases, then the person who's asking me the question, or maybe jointly, we'll try to push that into something which is closer to practice.
Practical, yeah.
Now, often I don't,
You're not involved.
I'm not involved directly, but then we can see how it performs, and then the feedback loop is often important. Because, and I can give one example, when Andreas Krause, who's now a faculty member at ETH in Zurich, when he was here, we had some algorithm which was trying to figure out how to place sensors in the most informative way. If you have only K sensors you can put down, where should you put them? And he actually went he went to Margaret Morrison and he figured out some sort of measurements, and he actually implemented those things. And it was very heartening to see that the algorithms did perform much better than the previous ones.
That must be very satisfying.
Very, very satisfying. Because frankly, sometimes as theorists, we can be in this sort of sound bubble, right?
Yeah.
We're not listening to the world. Now, I'm not saying that this is for everybody. Your interests may vary.
Right.
But for the kind of things that I do, I find it very enriching.
Yes. So, yeah, I guess both, maybe practical considerations and just like curiosity-driven theoretical, both are important.
Absolutely.
Right? Because there are also situations where some concepts were just introduced purely for theoretical reasons. One good example might be zero-knowledge proofs. When they introduced this, they had no idea the kind of applications that it would lead to. But it was a natural thing to study for them, and it was interesting theoretically. It was curiosity-driven in some sense, research that found amazing practical applications, that has found amazing applications now these days.
Absolutely.
So that's also important. But I do think, I also hear that, what you're saying, just directly talking to practitioners and what their problems are, and giving a theoretical eye.
And it really does depend on the person. I do enjoy talking to my colleagues who are not in theory, because the kind of questions that they are looking at spur ideas for directions to look in, for directions to investigate.
Right.
And this works for me. This may work for others. This may not.
Yeah.
And we all have to find our sweet spot, right?
Absolutely.
It's,
Great. So now let me ask you, what is the work you're proudest of?
oh man, proud and stuff.
So first of all, like, how many years have you been doing this?
We don't talk about that.
Okay, sorry.
I've been at Carnegie Mellon now 21 years.
Yes.
So we can calculate
Yeah,
by
I mean,
that.
I should have started with that. Yeah, you have been here for a long time. When was the first time you taught 251?
I taught it in the spring of 2004, I think.
Almost like 19 years,
Almost
basically
19
19 years,
yeah.
right? That's
And
amazing.
I taught it with Stephen Rudich, who
Yes.
actually developed the course
Developed
out here.
course, yeah.
And that was quite a thrill.
Yeah, yeah.
But,
So, okay, well, you know, you have 20 plus years of research experience. You've done a lot of amazing work, but does one stand out for you? Has it like a special place in your heart?
yeah, I'll say I'm proudest of all the works I've done with my students, because it's such a joy.
Yeah.
You know, working with students, it's a pleasure, right?
Can I say something? I kind of like predicted that you were gonna give this answer, knowing like how kind you are.
Oh, come on.
No, seriously, I was like, anyway, I just wanted to say that.
It's
Okay. Great. So now let me zoom back out a little bit, and let's talk about like theoretical computer science research in general.
Totally.
I mean, the field is not.
This on the web.
Okay, Siri, I'm not talking to you.
Siri's
It
feeling,
does it. It does it
left
also during lecture, by the way. Come on, it always wants to get involved. But okay, looking at TCS research, it's a relatively young field, I would say. How has the field, you think, evolved over time? Back in the early days, the fundamental questions, fundamental papers that sort of shaped the field. But now, like, where are we? What are like the main questions driving TCS, theoretical computer science research?
Right. So, thinking over all the years that I've been involved, and many years before that the theoretical computer science has been around, it's somehow the canvas is becoming broader and broader. Because when we first started, we were trying to understand computability. We were trying to understand very basic complexity questions. We were trying to understand, how does hashing work? Questions like that. I mean, deep questions, but still, the scope, the focus was somewhat narrower. But I think it's this relates back to the answer and the discussion that we were having earlier, that now more and more the scope is broadening. We are trying to understand computation in a much more general sense than we used to. So computation in economics, computations, quantum computation, these kind of questions were not there many years back.
Right, like algorithmic game theory, you could say, was born because we wanted to understand the economics of the internet.
Absolutely.
Right.
As Avram often says, we knew how to sort numbers.
Yeah.
But we didn't take into account how the numbers would feel about being sorted. It's like you don't want to be the last guy in the list, so you might lie about your own number.
That's amazing. Yes.
It's
and then what do you do, right?
now what do you do when people lie? What do you do?
Right.
Machine learning algorithms are now more and more. Actually, they've been for a little while. Social algorithms about social networks. These are questions that people have been looking at.
Right.
Robust statistics, which we would never have considered part of computer science maybe 20 years back, are now a solid part of computer science.
Right.
So I think the canvas is broader than it's ever been.
Right. And looking into the future, so we can see, AI, breakthroughs happening. Do you see AI having an effect on theoretical computer science research, and how?
So many different ways. Firstly, it'll inspire new questions that we'll ask and we'll answer.
To understand those AI systems.
To understand, right? Those AI systems.
What's going on
What's
with these
going
things?
on.
Yeah.
And the understanding is in two different ways. One is, why are they so efficient? Why are they so effective? But secondly, how is this training? Right now, the training is using very simple algorithms, things called stochastic gradient descent. How can this simple learning procedure give such amazing answers?
Right.
So I think the AI is going to affect it definitely in the questions and answers that we're going to get, but also in the techniques, the way we do things. Because with the AI engine as our ally in some sense,
Right.
we might be able to answer questions much faster, much better.
Yeah.
Technical questions that were more difficult, we might be able to just pass them on to a theorem prover, if you will.
Yeah. Yeah, I mean, so several things about that. In terms of AI being good at math, do you see it like actually advancing to a point where it's at human level of doing math or better?
Why not?
Yeah.
Why not? There are things happening right now that I wouldn't have expected in my lifetime. So never say never at some level. But it will require some amount of give and take with the sort of theory community, the broader theoretical computer science community, where we sort of contribute back and we figure out the best way for in some sense a pattern recognition system. My understanding, and this is almost a layperson or maybe a slightly educated guess, is that many of these chat systems, many of these AI systems are very good at figuring out patterns, nebulous patterns. But in order to prove things, it's not enough to figure out the patterns. We have to actually prove things. But combining them with theorem provers might be. And people are doing this.
I mean, I want to get into that. But before that, I mean, I could see, in some sense, like doing truly creative work, like getting to that point. I think this is just my personal opinion, but will require some time. Like I don't think it's like in the very near future. Although I can see AI system like ChatGPT developing enough so that it's like serves kind of like a student, where you may be given outline of a proof. You don't spell out everything, but here's like the high level steps that I think. Can you just now just write the paper for me? And then, I mean, that would be amazing. That would be the dream.
That would be great. And in fact, what the students can themselves do, it's not like we're replacing the students. We are just replacing perhaps some of the sort of grunge work or some of the more routine tasks.
And then you're left with the creative work. And
work.
That's the beauty of it. Yeah,
absolutely.
I think that would be amazing. And also with theorem provers, formalizing mathematics, there's a interesting development in that area. Lean is now extremely popular.
Absolutely.
And we seem to be at a point where we can take complicated proofs, human proofs, at the highest level and actually formalize them completely so that they can be checked by a computer. And this requires a reasonable amount. It doesn't require 10 years of work now, in 6 months or something, in months. And this will get better and better over time as the libraries improve.
And frankly, I would imagine that if these chat systems are good at comprehension of human language, I could imagine writing down a proof.
Yeah, and then they will
do the conversion into Lean, use the Lean system in order to verify it.
Yeah, exactly.
And maybe give a formal proof, and then come back. And this would be an amazing way in which we could verify human readable, human writable proofs.
Yes. I guess it could start with a co-pilot for lean.
Absolutely.
Which I don't think exists yet.
Maybe this is what we should be working on.
New project, new research idea. But then, yeah, I mean, at some point it could be like your interface
Totally.
with a theorem prover. So then, how do you see this affecting how we do research? Do you think, like, in the future, when you submit a paper, like, you have to submit like a formal one as well? Like, it has to be formally checked, otherwise it's not accepted.
This would be an ideal situation.
Yeah.
This is something that I have thought about again and again. So I have had the unfortunate experience of having written a paper and then gotten an email from a colleague saying, how do you prove lemma 3? It seems to be incorrect.
Right.
And here's the counterexample, and you read it and you say, oh man,
Yeah.
it's completely incorrect. So we had to withdraw the paper. And if you had a verified proof, this would not be a problem.
And this happens more often than people think. And probably there are lots of errors out there that not like even
Absolutely.
found.
And many small errors, that's fine.
Yeah, I mean, some can be fixed, but maybe, I mean, in your case, were you able to?
No, we had to withdraw the paper.
Oh, it's like, it really.
Exactly.
Wow, okay.
Yeah.
Because oftentimes, like, you can patch it some other way. But
Exactly.
yeah,
But no,
this was a fundamental.
that was a learning experience.
Yeah, okay.
But, oh well.
Yeah.
It happens.
And how do you think, like, all of this stuff that we've been discussing now will affect how we teach math and theoretical computer science?
Absolutely. It's a question I've been thinking about all through the course and through the past 2 semesters since all this has developed. So firstly, I think we can use it to be more effective teachers, because one thing that if we could provide, and this would be really good, is that the students might have this as a personalized TA,
Right.
where the students can give proofs and the system can try to at least point out some bugs as a first line of defense.
Right.
Now, of course, there is the sort of correctness aspect of it. Because if the TAs are wrong, in this case, this sort of automated TA, if it's incorrect, this can cause some problems as well. But once we reach a certain level of maturity, I can imagine this being a very effective way of students being able to chat with
Right.
a slightly more knowledgeable system.
Yeah.
And ask them questions and learn from it.
Yeah. I mean, it's good you brought it. It is something that actually I wanted to, explore this somewhere going forward. Fine tuning perhaps these large language models with, the data that we have, and can we create like a decent tutor, if you
Totally.
will. And that would be interesting for sure. And from the sort of formalizing proof side of things, do you feel like that we should start incorporating this stuff into our undergraduate curriculum? Is this like how students should get introduced to proofs, writing proofs, or it should be maybe something that comes after? Maybe
a little later, because right now, at least one problem I see with this is that there is a cumbersome aspect to this of formalizing proofs.
Yeah.
And if we could give some higher level abstractions that they could formalize their proofs in terms of, that might be okay. Right now, I don't think we are at that point, but maybe in a few years' time, if there were these higher level abstractions that the students could write in, I think it might be a good idea.
Yeah.
Because just like in a DFA, you make a DFA for a language, you can actually automatically check whether it's correct or not, assuming you know a correct solution. So the same way in which the student should be able to get back immediate feedback.
Right.
And, your proof is wrong here and here.
Yes.
Or you made a jump here and here.
Right.
I think that's very useful.
Yeah.
It's like a regrade, but almost a soft regrade.
Right.
And could be really fun. Could be really interesting to explore.
Yeah, things are changing. It's interesting. It's exciting.
It's fun times for us.
Fun times. So let me ask a different kind of question. So suppose you're a billionaire now. Okay, so you have $10 billion. And since you love theoretical computer science, of course, you decide to donate $1 billion to theoretical computer science research, of course.
I'm such a nice guy.
What's the most, you think, in your opinion, what's the most effective way to spend that money to advance theoretical computer science?
Yeah. So some of that money, it would be really nice to spend it in ways that we understand well. Having centers for theoretical computer science where students can go and hang out and do postdocs, and people have workshops and things like this. And the Simon Center at Berkeley, for instance, is a very good example of that.
Yeah.
Rutgers used to have DIMAX, which was a very nice example. But I think maybe now I feel like a considerable fraction of this needs to go into education. And education at all levels, and in creative ways, so that we have the entire pipeline is kind of strengthened.
When you say all levels, do you really mean like grade school, grade 1?
Yes, yes, because if we are to introduce computation and we need to introduce the necessary mathematics.
Right.
And our science and math teachers are amazing, but they could always use more help, right?
Yeah.
In fact, all our teachers could use more help.
Yeah.
And if we can figure out interesting, innovative ways in order to sort of make the material more approachable.
Yes.
Because the material is beautiful.
Yes.
It's my friends often kid me when I say, "Oh, the proof is so cute." But it is, right? It's like gorgeous proofs, and like the algorithms are wonderful.
Yes, exactly.
But it's like often we don't have the right background for it and things like
exactly. I mean, the way I like to describe this is like I feel like I claim that math is the ultimate expression of human creativity. It is, similar. It's art in that sense. It's similar to music and painting and things like that. But of course, it's not as easily appreciated. I mean, there is so much you need to learn before you can like read and understand the math proof. So like the public cannot like appreciate that, but everyone can hear like a beautiful song and appreciate that. You don't need extra training for that. But with math, to appreciate the creativity in math proofs and to see that beauty does require, unfortunately, a lot of like training, years and years of training. And even then you spend like months banging your head trying to understand the proof. But then once you see it, it's like, oh my god,
it's wonderful.
Like, just everything falls into place nicely. So yeah, it is absolutely beautiful. And to teach that material well, you need to know it well.
Absolutely.
Right. So then you need like teachers who know the material well. But one problem is that if they know the material well, they could make like 5 times more money in the industry.
And this is sad, right? Because a teacher should be
celebrated and valued properly.
Exactly.
And I mean, I feel like that's the main problem with the education system. But
but that's maybe a longer conversation.
So
another hour of
next episode on CS251. Okay, so let me maybe now get into some of the student questions that we collected. We're good on time. So actually, there's like one in the chat. I'll just grab that one. Should computer science become another core subject like math, history, etc.?
Why not?
Yeah, absolutely.
Absolutely.
I mean, for me, there's no doubt in my mind that it should absolutely be.
Absolutely. And sort of, especially hand in hand with mathematics, I think it would be it can be a great complement. Sciences in general. I think it definitely slots into the entire sort of STEM curriculum.
Yeah.
And we should explain all aspects of computation, the programming aspects, but the reasoning aspects,
but especially like the programming aspect can be like really plug and play for me. Like just like you learn math and then you'll use that math in your like chemistry class and biology class and other classes.
Exactly.
you can use your programming knowledge in the same kind of courses as well. Yeah, but absolutely. So there is another question. When did you know for sure that you wanted to work in academia and TCS specifically? I ask this because I have a lot of uncertainty myself as an undergrad.
So there's sort of two aspects, TCS and academia, and maybe I'll answer these questions separately.
Sure.
So TCS, perhaps I knew a little earlier, and it was because of one of my undergrad mentors. So during my undergraduate at the IIT in Kanpur, back in India, I had the chance to work on a summer research project, and my mentor was very formative, and they got me really excited about theoretical computer science. And I just got sucked in, and in some sense you see it, you know it.
Yeah.
I wasn't thinking too much. After that, I knew I had to do this.
Yeah.
But until then, I was actually a programmer. I used to do a lot of programming, and what I used to think of as hacking, though it's not really hacking, it's just programming.
Yeah.
And I used to really enjoy it. I was pretty good at it.
Yeah.
So, but then I decided I would do theoretical computer science. I came to grad school to do theory, and then I did theory. I enjoyed it a lot, and I had excellent teachers, excellent fellow students. But then when I was graduating, I wasn't completely sure I wanted to go into academia. I was worried. I was like, is this for me? Do I want to teach?
Right.
And so that was an interesting time. But then I did a postdoc at a place called Bell Labs in New Jersey, the famous research institution, because I thought maybe this would be a good place to work at. And interestingly enough, I really enjoyed it, but it made me realize I wanted to be back in academia. And it's difficult to explain why.
So that's a research lab.
That's a research lab.
It's not like you went to Google working as a programmer.
No, that is true. That's true. So I had it easy at some level. But still I realized that I missed the academic environment.
Yeah.
And so that's when I moved here. After a couple of years at Bell Labs, I moved here. And once I started teaching, I realized, okay, this is where I belong.
Right.
This is the academia is where I belong. So it wasn't clear. It was kind of a zigzaggy path, and portions were bumpy. And I won't hide that. It's maybe I should go and I should just work at a investment bank and make a lot of money, or go and work at Google.
Right.
Interestingly enough,
at that time there was. It was just starting?
It was just starting.
Okay.
So I actually went down to Mountain View and had a conversation.
No way.
Yeah.
Oh man, you would have been rich.
Yeah, well, but
wrong
decisions
in life. Okay.
When in the sort of lecture on Markov chains, we were showing the photographs of Larry and Sergey. It's not like I was meeting them, but I was thinking, well, if I had joined then,
right, man,
a different story.
Yes.
But this has been a fun ride.
Yeah. So actually, related to all this that you were saying, do you have like a personal philosophy on how you make decisions in life, right? Big decisions. And I see this a lot with students, like, they're at a stage in their life where they need to make big decisions. And sometimes that can be crippling, right? Like, you have different options. It's not clear which one is the best option for you. You can't see into the future, obviously. You don't know what these different paths will lead to. And you have to, make a decision under a lot of uncertainty. And, we all have to do it,
absolutely.
Of course. And I guess, like, we all have different, perspectives and philosophies on how to approach this. Some people like to minimize risk. Some people like to do other things. But what is your, do you have like a strategy here?
Yeah, not really a strategy. It is about risk management, right?
Mm-hmm.
And you have to find the right level of risk that you can tolerate.
Right.
One thing that one thing often I tend to do is I tend to think of how much risk I can tolerate and add epsilon more.
Mm-hmm.
And try to do go a little out of my comfort zone. Right. It's worked for me so far, so maybe I've been lucky, a couple of twists and turns here and there, but it's not easy. But as long as you're excited about it, because I feel like if I'm confident in my abilities, which to some extent, most of our students should be, because they're awfully smart, then as long as you're excited about it, chances are you will make this work. And some of the decisions would not work out, but yeah, I mean, the usual thing. I don't have a particularly well-formed opinion about this, or well-formed philosophy, but being ready to accept a little more risk than you think you can take. But, it's do what you love what you do kind of thing, and then hope for the best.
Yeah. I mean, so my, I guess, approach typically is like a greedy algorithm. Because, I mean, there is the fact that I cannot see into the future. I cannot know, like, in 5 years what's going to happen, in 5 years what I'm going to be interested in. So my philosophy has been, I'm going to just, do what excites me the most, what I love doing. Just thinking, not like 20 years down the line, but, I usually think like 3 to 5 years. And in 3 to 5 years, what do I want to do? What seems to attract me the most? But one, I think, like, important addition to this is that I want to put myself in situations where if things don't go well as planned, then I can pivot and I have options.
For sure.
Right? So that's sort of like my philosophy, like a greedy approach. Follow your heart, but you don't want to like corner yourself in the future.
Absolutely.
And as long as you have options in the future, even if things don't go the way you hoped, you can still
and not all decisions will work out just as you plan. But,
and definitely not try to optimize things, because you have to just accept the fact that you don't have all the information, you cannot optimize. And you have to be comfortable with that uncertainty, because that's what I think. Students are like thinking so deeply, like trying to optimize everything here and there. It's really kind of waste of time to think at that level, right? And you're stressing yourself out.
You're stressing yourself. So this is a phenomenon. I mean, this is overfitting, right?
Yeah.
You're overfitting to a poorly specified problem.
Right.
And really, you want to sort of have some amount of entropy in there.
Yes.
This is, this is principle known as regularization. You don't want to overfit. And I think it's a great strategy. Another thing that helps is being able to have a couple of friends who you can talk to and listen to people. But then eventually you have to make your own decisions, right? They can't help you. So that's
absolutely. So let's get some other student questions. What courses after 251 do you recommend?
Oh man, there's so many courses.
Yeah.
We have this sort of amazing collection of courses, right? So 451 naturally.
Yes. So before that you have to take 210.
You have to take 210. Yeah. And chances are many of our students were taking 210 and 251 at the same time.
Some are taking at the same time. Not a lot, but some,
Okay. And then 451, for sure. If you're interested in sort of complexity aspects, I guess undergrad complexity is a great course to take. PNC
Probability and Computing.
Probability and Computing. 259, exactly. And once you've taken this set of courses, maybe some of the sort of grad courses would be really fun to take, right?
And then there are also some topic courses at the undergrad level, like quantum computation, Ryan O'Donnell's course.
Exactly. He's teaching in next semester, right?
Yes.
Are you co-teaching with him?
Not quite, I guess. But it is a course. I mean, there was another question here, and I'll tie to that. If you could teach any other class at CMU, what would you want to teach the most? And for me, like, I really want to teach quantum computation at some point, because I guess, I mean, I love the topic because it's really like at the intersection of computer science, math, physics, philosophy, like all topics that I thoroughly enjoy. I don't claim to be expert in these,
no, but
like
that's
all
okay.
of them, but you know, I just love these you know, topics and the intersection between them, and that will be like very fun for me. So that's one course. So at some point, hopefully I'll get involved. And then also like cryptography.
Now, yes. So
Ayush, I think, is teaching.
Oh, excellent. So that's a great opportunity.
Yeah. I guess like Elaine is probably teaching something on blockchains. That's also like crypto, but maybe you know, more on the cryptocurrency side, blockchain side of things. But then I agree, like, you know, at some point, I think, you know, if you're really interested in theoretical computer science, I mean, and this ties into, like, you know, we'll tie this into another question, which is like, how do we get involved in research as well? If you're really interested in theoretical computer science, you want to get the core courses out of the way as fast as possible, like, you know, 210, 451, PNC, and so on. And then really get into grad level courses.
Absolutely.
And I think that's like a nice stepping stone towards doing research, potentially,
yes,
right?
For sure. Because, you know, just the sensibilities of these courses become different. The less hand holding, which can be good, but a little challenging as well.
Right.
But on the other hand, then the kind of questions that people are exploring in these courses are much more open-ended, much more research-oriented.
Yeah.
And they're giving you the right tools to dive into research.
Right.
So, for instance, there's so many grad courses, many topics grad courses, but in particular, I would give a shout out to Ryan O'Donnell's 751, right? A theorist toolkit,
right?
And then maybe I'll make a plug for my own 850 course,
right?
Which is advanced algorithms, which I view as if you take Ryan's course, it's the next step.
Okay.
And I think it's a very reasonable next step to take.
Right.
So that could be a very good 2-semester course sequence.
Fall, spring. Although I don't. Is your course in the spring or maybe?
It changes over time. It's not yet.
I guess it's not too important. But
right.
Yeah.
Right. But something like that would be very reasonable.
And so, just like to keep at this, if a student wants to get involved in research,
right?
Okay, so there are the courses, but then what?
Then you talk to somebody, and in particular, especially if you've done these courses and you've done reasonably well at these courses, chances are you know the professor knows you, so talking to them about a research project would be the natural start. And whichever direction you want to take, and it's very natural that you don't exactly know what you want to do, but the first few steps at research I find are fairly fungible. You know, you're picking up how to do research rather than how to dive deep into a topic. So you want to talk to your professors and find out what to do.
So what is your approach to advising undergrad students? You work with undergrads.
I've worked with some.
Are you currently working with someone?
Not currently, but the last was Chris Sealer, who was the 251 TA last semester. Head TA, in fact, yeah. And so I've had a bunch of our own undergrads, and I've enjoyed working with them. And so my sense is my feeling is to pick up a problem that doesn't require that much background, so that students can kind of dive in and get used to the sort of give and take of research in some sense,
Yeah.
the way it flows, and ups and downs and things like this. And often it's a fun experience both for them and for me, and it clarifies for them whether they want to do research or not. And Chris actually worked for several semesters with me, which was great, because at the beginning we picked up a little toy problem. We worked on that for a little while. We made some progress, but then his interests evolved, and so the questions we worked on could also evolve.
Okay. Yeah.
And then he could also, once he had the tools, he was also working with other people. So in fact, you don't have to work with the same person. You don't have to work with them throughout your undergrad experience.
Yeah.
In an ideal world, you would work with 2 or 3 different people to get the broadest experience you can.
Yeah. One thing I want to emphasize here is that, when we're talking about doing theoretical computer science research, or like math research in general, it does require quite a bit of background. And if you jump into it too quickly, you won't have a good experience, and it will not feel good, and you will have a wrong impression of what research is like. So it is important to be patient. I think at the early stages, it is important to be I would say just be a sponge and just absorb as much as you can. Take a lot of courses, get yourself ready, to do research, and then also once you do get into it, be patient. It's tough, it's challenging. This is not like solving homework problems. You're gonna spend months on a problem and not have much to show for it. It's quite, it happens, and that's the nature of the beast. That's what makes it rewarding, in my opinion, right? Like when you do get something, I mean, it's like that feeling is very beautiful, right? Like, you've discovered if you prove something new, right? You've discovered some truth that no one else had discovered before. And that's magical, right? I mean, that feeling, if you can get that, it's amazing.
And it's what keeps us going.
Yeah.
It's it's the harder the problem, the more you have failed ideas. Sort of 1% of your ideas might work.
Yes.
But you live for that 1%.
Yeah.
It's the thrill of the chase.
You have to be okay with that, though, right? I do feel like, it doesn't fit everyone's personality.
It definitely doesn't.
Like, some people like to see progress, like steady progress when they're working on something. And the nature of this is like, you don't always make progress, and there might be stretches of time where you have not made any progress or barely anything, right? So
yep. So it
happens.
Patience is very important, and
yes.
I completely concur with you out there.
Yeah. Okay, so we are last 20 minutes. Let me ask you a personal question. And maybe it's related to what we've discussed. Can you give an example of like a big challenge in your life, a big maybe failure even in your life, and how did you feel about it? How did you overcome it? What was the experience like?
Yeah. So the sort of one challenge I can definitely say was when I was finishing grad school, when I was very unsure about what I wanted to do. And there were all these sort of directions that were pulling me. There were interests, but there was also, you think, maybe there's a sort of greater financial benefit to doing one thing, or there's more excitement in doing something else. And it was a fairly stressful time for me. Now I think back and I realize I didn't really know how to handle it, but it was sort of not overthinking it was perhaps a sort of a good thing, and also sort of relying on one's friends and one's family. These things are important, and I think once you have a support system, and your friends and family are very important. So they kept me going for maybe 1 year of my life, and then things sorted out. And they didn't get sorted out by themselves because there were things that I was doing, but then things calmed down and then I could make more rational decisions. And so one can get stressed, and stress is terrible. And so what I realized was, things happen, and one has to deal with them. But you keep good people around you. Keep your friends and family around you. It's really
I mean, I guess like this is not uncommon. Like grad school. I think most maybe students at some point in grad school go through some rough patch. I think for me as well, like towards the end was also like, oh, what do I want to do now? What's the next step?
What's the next step?
And that required some thought, deep thought, I guess. And but again, just I went with like follow your heart kind of thing. But for some others, like maybe it's not the end of the PhD, but like maybe at the beginning, maybe they have a rough start. Maybe some of them at the middle, they feel like they haven't, made progress enough, and that can be like very stressful. We say these things just to point out that everyone goes through rough times. Like it's inevitable. But as you said, like if you have the right support system, it's just a period of your life, but then you get out of it and hopefully good things happen at the end.
In fact, I'm reminded of another thing now that we're talking. The first time I was teaching 251, and I came here, I said, I realized I wanted to be in academia, I wanted to teach. And I'm teaching 251 and it's this big class. And I realize I've not been trained how to teach.
Yeah, that's true.
It's like you've been thrown into the deep end of the pool. And that was a very stressful time. Because the students rely on you. And we as educators, we're supposed to do the best by the students. And it's a challenging course. It was very interesting. It was very rough at the time. But again, you think about it, you take a deep breath, and the students realize you're doing the best you can. So they'll cut you some slack. And, anyways,
like you have to support each other there. I mean, but it is an interesting phenomenon. Like like a very important part of our jobs is like teaching. But it's not like we've got any training on this. Like we just like learn it on the fly.
We had TA'd a course or two, but it's a different story.
It is interesting. But it's also true, I would say, like for me as well, one of the most I would say stressful times of my life was like maybe my first semester here at CMU as well. I was teaching 112, and that's even bigger course.
500 people.
Right? About 500 people. I mean, I wasn't teaching by myself, but still, it was a very intense experience, and a lot of pressure on your shoulders, of course, to do well. It's a very successful course, but it's a very intense course. The students are spending a lot of time. So so what you said with like first time teaching 251 and the stress of that really like resonates with me as well. It wasn't I guess like first time teaching 251 as well was also stressful for me. So my first year I taught 112 first semester in the fall and then 251 in the spring.
Oh my God.
You
survived.
I survived. I'm still here. And then 251 was also very stressful just because I guess like one of the key things about teaching well is like you have to know your audience. You have to know the students. And I just did not know where the students were. So I like my calibration was completely off. After one semester I could calibrate and I understood like, like these are the things that students find challenging, these are the things that students are okay with. But that first semester was in many ways, like for me it was kind of a disaster, but I survived. Anyway, but yeah, good. Let's see, we have a question here. As an aside, regarding the theorem prover comments earlier, a big recent thing in proof assistant land is the use of ML models as premise selectors, with Isabel and Hall and Thor, and just recently Magnus Hammer, this one I don't know, are really good, crazy good. Like, we've gone from being able to solve almost none of the archive of formal proofs problems to solving, I think, 65% now, and pretty
awesome.
fast too. So yeah, I mean, the marriage of machine learning tools with these formal proof systems.
Methods.
I mean, this is very promising for sure, and this it's going to lead to some very interesting stuff. Another question is, which experiences in your TCS journey made you really change your perspective of the field?
That's an excellent question. So one I can definitely say is the work I did for my PhD was on metric embeddings, which was at the time a very theoretical topic. And in fact, by the time I was finishing, it wasn't clear that this was going to be a sort of a mainstream CS topic, and it seemed like a niche area. And I did have a crisis of conscience. Why am I studying this thing? Am I just studying this for maths, which is fine, but and a couple of years later, somehow the results that people had been proving until then started to snowball into something much bigger. It became much more mainstream. And one thing I realized was that theory CS, so until then I used to have this feeling that, either you're working on the purely theoretical aspects or more applied aspects. But what made me sort of change that perspective was the realization that what you think is one can actually be completely sort of crossed over to the other side. So something that seems completely theoretical tomorrow might be very practical,
right?
Or at least has applications to practice.
Yeah.
And this is sort of an important realization, and I think this is one that we should keep in our mind. And another one is so our colleague Gary Miller used to have this sort of imagination in his mind that maybe tomorrow doing computing sort of a matrix, an inverse of a matrix, or solving a system of linear equations is going to be faster than computing max flow. It's like, what if that were the case? What could we do? And I always used to wonder, that seems like such a crazy idea. Gary is such a visionary. I wish he is true.
Yeah.
And today it is true.
Yeah.
For many kinds of linear systems, we can solve them much faster.
Right.
So, sort of thinking big and thinking outside the box.
Yes.
It's and sort of building on that. It's all reductions, right?
Yeah.
It's like, if you could do this fast, what else could we do?
Right. And
I've learned a lot from Gary, and this was one of the things that I'm forever grateful for.
That's great. Okay.
I should, how about you?
Yeah, well,
you should answer one of these.
Sure. I mean, I guess, like, from my perspective, just the realization of, like, what is important and what is maybe noise and detail is something I sort of appreciated more later in my life. And I didn't appreciate it, I think, in my PhD years. But yeah, it is possible to get into, like, sucked into some technical work and like trying to shave off some log n factor here and there. But then, you have to every now and then step back and look at the big picture view, and it's like, what am I contributing to this big picture? And I think, that kind of view is very important, and you have to remind yourself, like, these kinds of things maybe.
So, it reminds me of a little segue. And Manuel Blum, Turing Award winner, who used to have the next office,
right.
He had this thing that he would ask, oh, can you explain your research in like 15 seconds? An elevator spiel, if
Right.
you will.
Yeah. Yeah.
And I thought that was an amazing sort of insight into positioning your research, into understanding your own research.
Yeah.
Can you explain it in 15 seconds?
Yeah.
And don't
That's
you
good.
dare ask me to explain it in 15
I
seconds.
won't do
right
it.
now.
We're running out of time, but it's good. Like, I mean, I think the point is like you're in the weeds and like you get sucked into it and you do all this stuff, but like you have to remind yourself to like just step back and look at it from above and
exactly.
and
Exactly. And this is true not just in academia, in everything.
Yes, absolutely. Yeah, absolutely. One thing that I wanted to ask you, it's an interesting question that I sometimes get from the students, is suppose, a student really likes theoretical computer science, the ideas, the topics, the techniques, the skills and everything, but they don't want to get into academia. They don't want to be a professor. What options are there available besides academia for someone who really like loves and enjoys theoretical computer science and math?
So I think this is a pretty good time for such a profile, because I think a lot of companies are interested in having somebody who are sort of good problem solvers and who have a good broad understanding of theoretical computer science, broadly speaking, so that it's not just, and you can look at sort of slightly more researchy positions. So many of our companies, big companies, have research groups now. So that's good, because a few years back it was essentially maybe only 2 or 3 companies had research groups for CS. Now most companies have research groups in CS, or at least research e-groups.
Yes.
So I think especially if you're talking to any of these companies, maybe sort of finding out if they have a slightly more R&D group might be reasonable. And this is true even for companies which are not just, your big names, Google, Facebook, whatever. I should say Meta, I don't know. But even sort of smaller companies, or sort of companies which are very big but which are known for their CS focus.
Right.
I think sort of if you're talking to a recruiter, maybe also find out, are there opportunities? Because often there are.
Yes.
We just don't hear about it.
Yeah. Yeah, I think like even in software engineering or systemsy kind of work, there can be a sort of like a problem solving flavor to the work aspect of it. Like there are different kinds of like software engineering jobs. Like sometimes the most boring one might be like you implement other people's solutions, ideas, right? Like you're the person who implements it. But, you could be the person who comes up with the solutions, the ideas.
Right.
So, and that is, I think, in spirit, very similar to theoretical computer science research. Because oftentimes you will need to, take the real world problem, model it appropriately, find the right abstractions, get rid of the distractions, and then apply interesting problem-solving skills to find a decent, good solution, which hopefully then can be implemented in the real world.
Exactly, and it's sort of refined, and this is the sort of standard software development process, but just the problem-solving aspect is something everybody needs to do, and chances are it's being done much more broadly than
So to finish off, since we're last 2 minutes here, so this is basically like the end of 251 now. And you did mention this a little bit in the last live lecture that you gave, but like, can you summarize like the take-home message of the course? Like, what should students take once the course finishes? What are the things that you hope they will take with them?
Yeah, so there's so much in the course that I often feel like we might, as a student, one might think that there are all these sort of details that we taught them. And there are, of course, all the techniques we taught them and all the math we taught you and all the CS and applications and stuff like that. But frankly, it's essentially about how to problem solve with a CS perspective, right?
Yeah.
It's like how to take a problem, how to abstract it,
Yeah.
how to write down the question that you're trying to solve. Make sure it's the right question, which is often, the hardest part of our job.
Yes.
Then figure out a solution, then figure out a better solution, and then maybe figure out, maybe I can't do any better than this.
Right.
And it's the standard techniques. What's the simplest version of the problem you can solve? Can you give an algorithm? Can you give a lower bound?
Yeah.
Do bracketing, get better and better solutions. Try small examples. Sort of ideas like this. Sort of essential problem solving. And problem solving using all the mathematical techniques that we've developed. All the abstractions that we know. Reductions.
Right.
That's our biggest superpower, right?
Exactly.
Randomization. Right. Approximation.
Yeah. And I think just overall also just this rigorous thinking,
totally.
Whatever you do in life, right? Like, you are, in this world, you have abstractions of the real world in your mind. You make a model of it, and then you reason about that abstract model in your mind, right? And you want to have, reliable, accurate reasoning mechanism. You want to be, accurate and sharp with your reasoning tools. And I mean, for me, like not just one course, but like the undergraduate, experience overall, I would say the most beneficial part of it, I would say, was that like it made me much sharper in terms of how I, reasoned about real world situations. And I could see, like, when I was making an error in reasoning, I could see if other people were making error. I mean, I could, when I'm making some kind of reasoning, I know what my assumptions are. I know how I'm, applying my deduction rules to get to the conclusion that I need to go to.
Exactly.
This is like, whatever you do in life is absolutely crucial, in my opinion, so that, you cannot be fooled and you can make reliable conclusions about things.
It's like, now when you write a piece of code, even though we don't ask you to prove it, you should prove it to yourself.
Right, exactly.
And not just for a piece of code, for every action you're taking. You're saying, this is where I'm starting from, here are the possible outcomes.
Yeah.
And let's figure out what the probabilities are.
Exactly.
What the outcomes are.
And you want to have the tools to be able to, figure these things out. So I completely, but I mean, let me also add one more thing to this, which is that, I always say, like, the most important thing for me that students get out of this course is just like, it's more emotional. It's just an appreciation for, science and how beautiful science and math is. And if we, can manage to somehow show the students that, this stuff is really cool, worth learning, and, it ignites the intellectual curiosity of the students. Like, that's my number one thing. If we did that, then, that trumps everything else, because life is a lifelong learning journey. Right, so if we excited you, then you will learn. Like, even if you didn't learn it perfectly in 251 or something, you will learn eventually, because you enjoyed it. You enjoyed learning about it.
It's like going on a hike, right?
Yeah.
We went on this hike together.
Yeah.
And some bits were too intense for some of us.
Yeah.
And as somebody who has a fear of heights, I completely empathize.
Yeah.
And some bits were great, and some bits were slower, and others were faster. But as long as you just see the beauty of the thing.
Yes, exactly. That I would say is number one. And then number two is, I think, like, reasoning skills, like the skills you learn. Students shouldn't think too much about, like, the particular topics or 7-tuple definition of that's not the point, right? Like the DFA 5-tuple, that's not the point, right? It's really more about the skills and just getting to see some of the greatest intellectual discoveries that we've made, and it's really beautiful. Last question: what do you love about CMU?
The students.
Yeah.
I mean, my colleagues are great. The campus is very nice. Whatever. The students, they make it real, right? And they make it worthwhile. It's such a pleasure.
Yeah, I mean, actually, my answer is basically would be the same. I would say like the people. Students for sure, colleagues for sure, and just the community.
The community is great,
and that's number one thing for me as well. Okay, we are out of time, so thanks everyone for joining.
Thank you.
So I guess we'll see you guys next week. I mean, we'll have office hours
for sure,
and so on.
For sure.
But for now, this is it. And I guess I'll just say, like, our doors are open, right?
Come by.
Keep in touch.
Yeah. Also come by later on, right? Let us know how you're doing.
Yeah. Absolutely. That's what I mean. Like, after the course finishes, drop by. Let us know how you guys are doing. Awesome. This is it for now then.
Thank you, Anil.
Yeah, thank you. Pleasure.
Hey, thank you all. See you. Bye-bye.